Flip a switch and a bulb lights instantly. But what's actually moving in that wire, what pushes it, and what slows it down? Answer those three, and all of electricity opens up. In this video, we'll build current potential difference, Ohm's law, and resistance, each from scratch in plain language. Let's start with what's flowing. Inside a metal wire are countless tiny charges, electrons, that can drift along it. When they flow in one direction, we call that an electric current. Current is just the rate of flow of charge, the amount of charge passing a point each second. In symbols, current I equals charge Q divided by time T. Its unit is the ampere. 1 ampere is 1 coulomb of charge flowing per second. By convention, we mark current flowing the way positive charge would move, opposite to the electrons, but that's just a historical choice. Charge only flows if there's a complete unbroken loop, a circuit. Break the loop with an open switch and the current stops instantly. The cell, or battery, is the pump that keeps the charge moving around the loop. Think of it like water. The wire is the pipe, the charge is the water, and the cell is the pump that keeps it circulating. So what does the cell actually provide? A push. That push is the potential difference between 2 points, the work done to move each unit of charge between them. In symbols, voltage 5 equals work W divided by charge Q. Its unit is the volt. 1 volt means 1 joule of work per coulomb of charge. More volts, a bigger push, more current. The cell creates this potential difference that drives the whole circuit. 2 meters let us measure these. An ammeter reads current, and it goes in series, in the line of flow, so all the current passes through it. A voltmeter reads potential difference, and it goes in parallel, across the 2 points you're comparing. We draw circuits with standard symbols, a long and short pair of lines for a cell, a circle with an A for the ammeter, a circle with a V for the voltmeter, and a zigzag or rectangle for a resistor. Now the law that ties voltage and current together, Ohm's law. At constant temperature, the current through a conductor is directly proportional to the voltage across it. Double the voltage, you double the current. Write it as V equals Y times R. On a voltage versus current graph, that's a straight line through the origin, and its slope is R. That R is the resistance, the conductor's opposition to the flow of current. Rearrange Ohm's law, and resistance is voltage over current. R equals V over I. Its unit is the ohm. A bigger resistance means that for the same push, less current gets through. A thin, resistive wire chokes the flow. A fat, conducting wire lets it rush. What decides a wire's resistance? 3 things. 1. Length. A longer wire has more resistance because charge fights through more material. Resistance is proportional to length. 2. Thickness. A thicker wire, larger cross-sectional area, has less resistance. Resistance is inversely proportional to area. 3. The material itself. Put together, resistance R equals RO times length L over area A. That REO is the resistivity, a property of the material alone, measured in ohm meter. Metals like copper and aluminium have very low resistivity, which is why wires are made of them. Insulators like rubber have enormous resistivity, and alloys like nichrome have high resistivity that barely changes with heat, perfect for the heating elements in toasters and irons. Let's use Ohm's law. A 12-volt battery drives a current of 3 amperes through a resistor. What's its resistance? R equals V over I, 12 divided by 3, which is 4 ohms. And if you doubled the voltage to 24 volts with the same resistor, the current would double to 6 amperes. Exactly what Ohm's law predicts. Your turn. The question's on screen. Pause if you like, but try it first. 10 seconds, go. Use R equals V over I. The voltage is 12 volts. The current is 2 amperes, so R is 12 over 2, which is 6 ohms. The answer is 6 ohms, option A. And that's the foundation. Current is flowing charge, potential difference is the push. Ohm's law links them through resistance, and resistance depends on length, area, and material. In the next video, we combine resistors and see what current does, heat and power. Free notes with practice questions are in the description. Subscribe for part 2. This is Clarix. Keep going.